So, hello everybody, and welcome back to our class. Today, we will finish chapter number 5 about the probability. Last time we started the probability, and we know now how to find the probability. We have three uh, methods to find the probability: the classical probability, the empirical or relative frequency probability, and the subjective probability. Of course, subjective probability, we can find the probability with this method based on your experience, your feeling, your guess, your information you have, because in most cases you don't have any experiment in there. But for the classical method, we suppose that all outcomes in the sample space has the equal likely chance, same chance to selected. So in this case, based on these assumptions, we calculate our probability. And the empirical or relative relative frequency probability method, we use here the frequency table to find the probabilities based on the relative frequencies. Here, of course, we have an experiment to do, and then we can find the probability from them. Also, we talked about some important rules, like the complement rule, the addition rule, and the multiplicative rule. And also we talked about the disjoint events, or sometimes we call it mutually exclusive events. When we have two events, for example, A and B, we can say they are mutually exclusive or disjoint if there is nothing common between them in this case. Okay. Also, today we will continue the probabilities with the very important rule. We call it the conditional probability. So what that means? That means all probabilities we try to find the last time, we call them unconditional probability. Unconditional probability. But today you will know how to find the probability under a conditional. Okay? This method based on what? In advance, you have an information about a probability of an event. And based on this information, you will find the probability for another event. Again, you have an information about specific events. Based on this information, you will try to find the probability for another event. Okay? Of course, this will boost or support your probability. When you find it, then you use the unconditional probability. As you can see here, for example, if you have A and B, two events, for a conditional probability of event A, given that event B has occurred, just look at this, given that event B has occurred, so we have this information in advance. Okay, what is the probability of A? First, we write it like this. So the probability of A, and then vertical slash B. Vertical slash here mean given. Okay, so the probability of A given B. So which one happened first? B occurred. And this is the information we already know. What is the probability of A in this case after B occurred? So to find out this probability, you apply this rule or function. The probability of A and B divided by the probability of B. Okay? And as you can see here, down here we have what? The probability for the conditional event, the given event. So what that means? That means if we need to find the probability for B given A, the equation now will be, or the rule will be, the probability of You can see B and A. Doesn't matter if you say B and A or A and B, because both means the common events between them. Okay? So this is B and A. Or you can say A and B, same thing, divided by the probability of given events. So the probability of A. So look, we divided by what? The probability of given events. So this is the rule. Okay? So if you have another example, what is the probability of D given C? So the rule now will be the probability for D and C divided by the probability of C, the probability of given events, as you can see. So this is the rule, okay? But the more important thing to understand what that means. That means C occurred before A. And based on that, we try to find the probability of A, okay? So this is the chart for this type of probability. As you can see here, the first probability up there, the probability of A and B. This is the probability of common events between A and B, and divided by the probability of B, and this, of course, the given events we have here. Okay. So as you can see from this chart, we already have some information about B. We have the information about B. And we need to find what? The probability for this part. What is A now? What is the probability of A? So we have some information about B, and we have here a link between A and B, this small part here and here, we already know that. So what is the probability of A? Of course, this is support your expectation. Always you will find the conditional probability has higher probability than unconditional probability. What that means? That means if you try to find the probability of A without knowing anything about B, always will be lower than the probability of A given B. Okay? But because you know some information in advance about B, which has a small part of information about A, this one, okay, as you can see here, you can find the probability of A with higher probability than the unconditional probability. Okay, so this is the nice part about conditional probability. For example, suppose we have here this contingency table. This contingency table shows the level income and whether a taxpayer is audited by the IRS. So as you can see here, you have these levels under 200,000, from 200,000 to 1 million, and more than 1 million. 3 levels of income. Okay, and for the audited, okay, we have yes, it's audited by the IRS, or no. Okay, and we have here the probability for each events we have, as you can see. Okay, so these are the events for each, the probability for each events we have in this table or this scenario. Okay, the question is, what was the probability of being audited given that the income was at least 1 million? So as you can see here, given, very important word, that means we are dealing with conditional probability. So given that what? Given that the income was at least 1 million. Okay? So here we have two events. The first one, we need to find the probability of being audited, which means audited is yes. This is event A. You can say event C, event D, whatever. It's your option. This is just a symbol for the event. Okay? And for the second event, the given one or the conditional one is what? At least 1 million. So that means the income is greater than or equal to 1 million, as you can see. Okay? So what is the probability of A given B? Because this is what we need to find. What the probability of being audited? A given B. The income was at least 1 million. Okay? So apply the rule. The probability of A given B is the probability of A and B divided by the probability of B. Okay? So we will return to our table to find the probability of A and B. A and B. So where is A and B here? A is audited. So we will look at this column. Yes, it's audited. The tax buyer is audited. Okay? And what? The level of income greater than 1 million, right? Which one? This level. This one. More than 1 million. So where is the common event? Because the probability of A and B is what? The probability of common events between them. Where is this probability? Here, in the middle, between them, this one. Okay, so this is the probability of A and B. This one, okay? So this is the first probability. What we need else is the probability of B. What is the probability of B? What is B? B, the income is greater than 1 million. Okay? Regardless the type of audit. Okay? If it's yes or no. So where is this probability? Where is this probability? It's here. This one. So this is the probability of B. So all you need is to divide 0.00027 by 0.00249, and you will have the conditional probability like here, as you can see. And then this probability is 0.1084, or you can say 10.84%. Okay, so this is the probability of the tax buyer being audited, given that the income at least 1 million. Okay? Okay. On the other hand, suppose I said to you, what is the probability of being audited? That's it, without it given any information. So from the table, you will go to what? To yes, audited, right? This one. And you will take what? The total here. This is the probability of A. Look at this probability, it's what? 0.00964. So if you multiply it by 100, so it's what? 0.9, right? 64%. So which one is higher? Probability of A or probability of A given B? Which one? Of A given B. Why? Right? Because the information we already have in advance about B helped us to predict more about A. Right? And you, as I said to you, always find this. The conditional probability always higher than the unconditional probability. As you can, which we can rewrite that by this way. The probability of A given B always greater than, or sometimes will be equal And you will know after a while when will be equal probability of A. Okay? This is the conditional probability. This is unconditional probability. Okay? Of course, when you try to predict something, when you have background or information about it, it's better than when you try to predict the same thing without any information, right? Of course, it makes sense. Another example, the triple blood test for Down syndrome. As you can see here, we have a study of 5,282 women aged 35 who over analyzed the triple blood test to test its accuracy. We have here the blood test result, positive and negative. And also we have if the woman has Down syndrome status, so we'll say D, Down, or it's not affected, so we have the complement D, C, and affected. And we have here the frequency for all these combinations, as you can see here. Okay. Oh, I said probability. I'm sorry. This is the number, the number, the number, the number, and here the number. This is the number of women who has positive blood test and they have the Down syndrome. This is 6 here. This is the number of negative results and the Down syndrome status already exists. Okay, as you can see, and the same thing for here and here. Okay, so these are the numbers. I'm sorry if I said the probability. These are the numbers or the frequencies for each status. Okay. Okay. So here you have the four, as I said to you, the four status here. We have positive test result. This will have the condition is present. The negative test result is that the condition is not present. False positive test states the condition is present, but it's actually absent. And the false negative test, the test here stated that the condition is absent, but it's actually present. Okay, as you can know, for any test we have some errors, right? Okay, now the question is, assuming the sample is representative of the population, estimate the probability of the positive test for a randomly chosen pregnant woman 35 years or older. So we need to find what? The probability of a positive test for a randomly chosen pregnant woman 35 years or older. And this, of course, what? Regardless if she has Down syndrome or not. Okay? So, where this probability? We can find this probability by dividing the total number of positive tests. Where is the total? The total is here. By the total number of all women we have in this study, this number. Okay? So you have 1,355 divided by the total number 5,282. So it's about 25.7%. So this is the probability of positive test. For any woman, we'll select randomly from this sample. Okay? Next question. Of course, what type of this condition, this probability? It's the unconditional probability. Okay. Now, another probability. Given that the diagnostic test result is positive, so it's given. As I said to you, this word is very, very important in our questions here. Given. Just you see given, that means we are dealing with conditional probability. Okay. Given that the diagnostic test result is positive, estimate the probability that Down syndrome truly is present. So we need to find what? The probability that Down syndrome truly is present, given that the diagnostic test result is positive. Okay, so this is what we need: the probability of Down syndrome truly is present, given that the test what is positive. So apply the conditional rule, the probability of D and the positive. This is the, we can find that from the table, divided by the probability of positive. Okay, we already found the probability of positive from previous question, as you can see here. This is the probability of positive. As you can see, we found that here, it's 0.257. And we need to find the probability of D and the positive. D and positive, the intersection between these two events. So where we can find this? So the number of subjects that are common between these two events is here, positive and D. So this number 48 divided by the total number here. This, of course, will give us the probability of D and positive. D and positive. Okay, so it's 48. So this probability is 48 divided by 5,282. So you will have 0.0091. Okay, divided by the probability of positive. We already, as I said to you, we already have this probability from previous question. Okay, so you will find what? The conditional probability here is 3.5%. Okay, so this is the probability that Down syndrome truly is present, given that the diagnostic test is positive. Okay, as you can see. So as you can see, if you try to compare between the probability of D, okay, and the probability of D given positive here is what? 3.5, and the probability of down here, of course, you will divide 54 by the total number here. Okay, you will find that the unconditional probability is less than the conditional probability in this case. Okay. So we return again here to multiplicative rule. Last time, when we have the multiplicative rule, it was for the independent events. So last time in the part 1, the multiplicative rule was for what? The independent events. What are the independent events? Do you remember? There is, if you have A and B, two events, we can say they are independent if occurring one of them will not change the probability of the occurring of the second one. So they are independent. Like what? Like tossing a coin 2 times. Okay? The results here are independent. Okay? Right? The first one is a half, the second one also is a half. If you are interested in the number of heads, for example, or something like that. Okay? But now the events are dependent. The events are dependent. In this case, what is the multiplicative rule now? So as you can see, the multiplicative rule try to find what the probability of A and B. Like the previous one as well, when we have independent events. Also, we need to find the probability of A and B. Okay? So we need to find this probability. What is this probability now? When we have dependent events, it's the probability of B times the probability of A given B. Okay? Okay, from where we have this rule, it's from here. The conditional probability. The conditional probability is what? The probability of A given B is equal to the probability of A and B divided by probability of B. All you need is to do what? That's a cross multiplication. Okay, of course you have here 1, multiply this by this by this, so you will have our rule as you can see. Okay? Okay, same thing. The probability of A and B is probability of A times the probability of B given A. Okay? So don't confuse between them. Because we have here A, you will multiply the probability here for A. Because we have here B, you will multiply here the probability of B. Okay? Okay, so this is the multiplicative rule. Of course, here A and B are not independent events. That means one of them happened before the other, and because the first one happened, it's occurred effect on the second probability for the second events. For example, Novak Djokovic, he is a 2040 men's champion in the Wimbledon tennis tournament, England. Okay, he made 62% of his first serves, and he faulted on his first service the other 38% of the time. Given that he made a fault with his first serve, he made a fault on his second serve only 4.5% of the time. Okay, assuming these are typical of his serving performance, what is the probability that he makes a double fault when he serves? Let F1 be the event that Djokovic makes a fault with the first serve, and let F2 be the event that makes a fault with the second serve. Okay, so we already know the probability for the fault of the first serve from the scenario, this one, and the probability that the second serve is fault, given that the first serve is fault as well, is okay. So now we need to find the probability that the first serve is fault and the second serve is fault. Because they are not independent events, so we will apply the multiplicative rule for dependent event. So this will be the probability of F1 times the probability of F2 given F1, because F2 here is fault, given that F1 is fault as well. Okay? Okay. So all you need to multiply this by this, so you have the probability that he will have double fault in the serve, it's 1.7%. Something I talked about last time, sampling with or without replacement. It's a very, very important thing here, because we have completely different probabilities when we perform the experiment we have with replacement or without replacement. For example, suppose we have here a box. This box has 3 blue balls, as you can see here. Okay? What is the probability of getting one ball randomly from this box? So the probability is what? Is 1/3, right? This is for any one of them. Okay? So if you need to take a ball randomly from this box, the probability will be 1/3. Okay? Suppose you wanted to take another ball from this box. Okay? Look at this part without replacement. What that means? That means you took the first ball and you will keep it. You will not return it to the box, and you will take another one. So here, the number of boxes of balls here reduced by 1, right? So now the second ball will be what? 1 over 2. This is the probability. Okay? This, when we say without replacement, that means you will not retain or put the ball back in the box. Okay? But if I said with the replacement, okay, so the probability for the first one still the same, 1 over 3, and then you will return it. And the probability that you will get another ball also will stay the same, 1 over 3, because you put it again back in the box. Okay? So this is the difference between replacement and without replacement. Of course, in many sampling processes, once subjects are selected from a population, they are not eligible to be selected again. In most cases, we do something like that. And of course, this is the sampling without replacement. That means we will have different probabilities each time we will try to select the different subjects from the same categories from the population in this. But if we have a rule that tells that you allow the subject to be returned to the population, so that means there is a chance that the same subject will be selected again. In this case, we have the same probabilities. Each time we will try to select the subject from the same categories in the population. Okay? So this is the difference between replacement and without replacement sample. Okay? So how we can know if A and B are independent or dependent events? In previous part number 1, we said that if A and B are independent events, so the probability of A and B, this left side, is equal to what? The probability of A times probability of B. So if these two sides are equal, okay, that means A and B are independent. But suppose we don't have unconditional probabilities. These are unconditional probabilities. But we have conditional probabilities. We have what? Conditional probabilities. So if the probability of A given B is equal to the probability of A, or the probability of B given A is equal to probability of B, so here we have independent events. That means, for example, this one, occurring of event B doesn't affect an A. Okay? So B happened, doesn't happen, it doesn't matter. The probability of A is still the same. That means this independent events when we have something like that. Okay? Or this is our test. You can check that. To determine if events and B are independent, you have 3 things. If probability of A given B is equal to A, you can check that. If probability of B given A is equal to probability of B, is the probability of A and B is equal to probability of A times probability of B. If one of them is true, so the others are true. So that means A and B are independent. If one of them is false, so A and B are not independent events. For example, here, if you remember, this is our same example about the Down syndrome test again. We have here the probabilities, and we want to check, are the event positive? This is the positive test, result test. And the D, which means this is, we have the status is already present. Independent or dependent. So here you have, of course, our 3 rules. You can check, pick up any one of them and try to apply them. So for example here, in this example, we will try to check if the probability of positive given D is equal to probability of positive. So if we return it to here, the probability of positive given D, positive given the, okay, so this probability of positive given the is equal to the probability of what? Uh, Positive and D divided by probability of D, right? Right? So the probability of positive and D, this one, 0.009. The probability of D is here, 0.01. Okay? So of course this will give us the probability of positive within D, okay, which is 0.9. Okay? If positive and D are independent, should be this number is equal to the probability of D. What is the probability of D? This one, right? 0.01. Of course, they are not equal. So in this case, positive and D are not independent even. They are dependent evens. Okay? Also, you can check any you any two events here with any rule we have about the independence. Like what? Suppose you wanted to check if the probability of positive and D, of course, if they are independent, should be what? The probability of positive is times probability of what? Of D, right? This is another rule. We have three rules. You can, as I said, you can pick up any one of them. Suppose you wanted to check the same problem here, but with this rule. So what is the probability of positive and D? It's here. Again, 0.009. So when you multiply the probability of positive, which is 0.01, times the probability of D, the positive here, I said 0.01. It's here 0.257, 0.257, 0.257 times probability of D 0.01. Of course, it's not equal to 0.009. Completely different, right? So in this case, again, positive and D are not independent evens. They are dependent evens. Okay? Is a coincidence truly an unusual event? Okay? So here we are talking about that sometimes things around us happen, and it's not surprising to have a pattern about it, and this pattern is unusual. Okay? Like what? For example, let's take an example directly. This is an example about matching birthdays. What is the probability that at least two students in a group of 25 students have the same birthday? What do you think? This probability would be high, low? What do you think? Very low. So you said very low, right? Okay. Okay, let's try to calculate this probability. So first of all, the probability that at least two students in a group of 25 have the same birthday, we can find it by this way. The probability at least one match is equal to 1 minus, that is the complement rule, that the probability no matches. Okay? And to find the probability of no matches birthdays, in this case for the 25 students, okay? So that means, of course, these are independent days, okay? Independent days, and we have 365 days in the year. Okay, so this probability we can find it by this case. The probability for 364 divided by 365. They are independent days times 363 divided by 365 times 362 divided by 365. You will continue by this way until you have, because we have 25 students, so you will do this for 24 times. Okay? Oh, let me try to say, suppose you have just two students, just not 25, two students. And we wanted to find the probability that these two students have the same birthday. So you will find the probability for no matches. No matches, how many days? No match? How many days in this? You have 365 days. Right? If these two students have the same birthday, so the remaining are not, right? So we have 364. Do you see what I mean? So this is the first, this is the probability that 364 days will not match the same birthday for two students. Okay? Now we have 1 day out of all the other days. So we have now 2 days actually, not 1 day. One is matches. Any day during the 364 not matches. Another day through 300, the remaining 363. So we have this. Another one, 362, and so on until 300, I think 41 divided by 365. Because we will continue by the same way 24 times. Why 24 times? Because we have 25 students. Okay? One, we suppose that one it matches and the other are not matches. So we will reduce this by 25 times. Okay? As you can see here. So the probability of no matches will be, as you can see, like this. You will go here 24 times. Okay, so you will stop at 341. So this is the probability of no matches. Okay, no matches. So the probability that at least one match, just one match, okay, is 1 minus the probability of no matches, right? So will be 1 minus the probability of no matches. So it's 0.57 or 57%. So in this example, we have out of the 135 space shuttle missions, there were 2 catastrophic failures. What is the probability of at least one failure in a total of 100 missions? Okay, so here we will suppose that S1 denotes the event that the first new mission is successful, that S2 is the second new mission is successful, and so on until we have S100, that the event that the mission 100 is successful. Okay, we need to find here what? At least one failure in the total of 100 missions. So again, you can use the complement rule. So at least one failure is what? 1 minus the probability there is no failure. All missions are successful. And because these missions are independent, so we will use our multiplicative rule. Okay? So this probability of 0 failure, or the probability that all missions are successful, this one is the probability that The first mission is successful, the second mission successful, the third mission successful, until the last one is successful. Again, these are independent events, so you will find the probability for each one of them. Of course, what is the probability that the mission is successful? We have here, out of 135 space shuttle mission, there were 2 failures. So what is the successful? Right. So the successful is 133 divided by 130 what? 35. This is the probability of success in general. Okay. So that means you will find this 1 minus the probability of successful here 100 times, right? So it's 1 minus 0.7. Of course, this will give you 0.971. So you have here this probability. So this is the probability that at least one failure, at least one failure. Look at the probability, 94.7%, at least one failure. Well, at least one failure means one failure, 2 failures, 3 failures, until 100 failures. So the probability here is so high. Again, it's not reasonable, right? Why? Because when we try to answer on these questions, we have these assumptions. First, same successful probability on each flight or each mission. Okay? And of course, this is not true. In reality, we have different probabilities. We assume that the missions are independent. Okay, and this also is not true. Why? Because these assumptions are suspected since other variables like what? The temperature at launch, the experience of crew, the age of craft used, all these variables ignored. Okay, so you have to collect some more information about the successful, if any, mission by collecting information about these variables, and based on this, you find the correct probability. But when we calculate the probability like this, we have just it's based on what? On 2 things. The number of successful missions in the past, and we assume that all missions are independent. And of course, in reality, it's not like that. Okay? So that's it for today.